Hey guys, it's Mr. Sheeline here. This is going to be the lecture video that's just going to be covering roughly about half of the notes that you should have gotten on the last in-person day. If you're absent, we're just going to be going through the first half, and I explained it in class, and pretty much just simply we're going to stop in at the slide where it says forces in circular motion. We're going to be stopping there. And we'll get to that on a later date. So I just want to focus in on the this first portion, the just more or less just talking about describing what uniform circular motion is. Okay, so let's just go ahead, jump straight into it, and take a peek here. Now, okay, so uniform circular motion. So what is it? So there are different numbers of forces that we're going to be looking over, and there's going to be a new set of material that we're going to be studying. Now, one of them is going to be this force that you may have already heard of. It's what's called the centripetal force, and it is what is referred to as the center seeking force. Now, we'll get to, what that is, like more to what that is. Sorry for the bell. We'll get to more to what that is later on in the set of notes. But for all you need to know, this is the force that is moving towards the center of the circle or the path of motion, which is circular. And it's going to be depicted as this guy right here, that red arrow pointing towards the center of our circle. Okay. And another thing that we're going to be getting into, and this is really what we're going to be focusing in on this first portion, it's going to be the tangential velocity. So it's this guy over here. It's this right here. And it's what you should have seen in the little plate activity that we did as like an engagement activity. It's the one where you had the ball bearing inside the plate. And where you had to make the prediction, and then you use the plate that had a quarter of it taken out. What you should have seen is that when the ball was moving around the plate, that it was, it was spinning like this. But then once you cut out a quarter of it, what you should notice is see that it moves in this direction. Okay, it's tangential. The velocity is tangential from the surface of the circle. And you would have seen the same thing, or what you should have seen the same thing with the rubber stopper as well. Okay. Now, this is referred to, or tangential velocities are instantaneous velocities, which makes sense because remember, velocities, and it's kind of, in a way, it's hard to get an average velocity, though we can have one. It's difficult a little bit more difficult and trickier to use. We won't get into terrible specifics about it, but anyway, what makes pretty much every single velocity an instantaneous velocity is just the fact that, velocity is, the velocity is the rate in which an object changes its position in relationship to time, distance, and direction. And so here we're changing direction all the time. And so pretty much every single point in which you could take a snapshot of your velocity, it would be an instantaneous velocity. And that has some ramifications that we'll get into in not too much longer in this video. Okay, so these are the two first things that we're going to be looking at here. And we'll have to, for the most part, just have in the back of our brains, and then what we're going to be able to calculate here in a bit. Okay. So the speed and radius of an object remains constant while it is in motion. Okay, so the speed and radius of an object remains constant as far as when we're talking about uniform circular motion. Emphasis on the word uniform. So this is, thinking back to just, let's think back to Unit 1. Just get rid of circular. Remember, we were looking at uniform motion. It's just motion that does not change direction, or it does not change the rate in which it's moving. Okay. It's moving in one direction, and it's moving at a constant velocity. And that's what we're going to be practicing here, to keep things a little simple, to keep things a little bit not so complicated. Okay. And what else doesn't change is the fact that the radius doesn't change. So think about it. If you're right here, and let's say this is what you did for the rubber stopper, okay, the length of your string did not change. So the radius did not change here. Okay. And then at the same time, arguably speaking, neither did the speed. And that's what we're going to be looking at. Instances where, and scenarios where we have an object that is moving in a circular path, where the distance from the center, the radius, does not change, and where the velocity, the tangential velocity, just does not change either. Okay. Now, velocity vector changes because the direction changes. So what kind of impact will that have? Well, let's kind of continue down this rabbit hole and kind of think about that. So uniform circular motion describes, for the most part, a particle moving at a constant speed in a circle, which is what we just kind of talked about last time, or the last slide. Okay, and it covers the same linear distance in each second. So an example, turning around a corner in your car, planets orbiting, running around a circular track. These are examples where you have circular motion and where you have, for the most part, you have what's, constant or a linear distance, a relatively similar or same radius and speed in which something is moving around a center point. Now, did a whole lot of kind of reiterating, and maybe that's a bit too confusing. So let's now just kind of keep those in the back of our minds and move on to something we're actually going to calculate, something we could sink our teeth into. And that's going to be acceleration. So now the question that you should be asking yourself here is, how can there be acceleration if there is constant velocity? Because remember, acceleration is just the change in velocity of a moving object. So if we don't have a change in velocity, in other words, if we're working with constant velocity here, constant tangential velocity, how in the world could we have acceleration? Oh, it's a good question. And it's simply answered as such. So a moving body undergoes acceleration if its speed or its direction changes. And we established early on that we're changing direction all the time when we have something that's exhibiting circular motion. Okay. So because of that, we have this forever changing velocity, though it is somehow constant at the same time. We have acceleration here due to that change, mainly in the fact that it's changing direction. Okay, and so we would say then that uniform circular motion produces what's known as centripetal acceleration. So let's take the word centripetal force, and now let's substitute force for acceleration. Substitute acceleration for force. So centripetal force was a center-seeking force. So centripetal acceleration is going to be a center-seeking acceleration, okay? Or you can think of it in this way. Centripetal acceleration is just the acceleration that plays the part in the centripetal force, because they're both center-seeking. The object in which is, moving in the circular path has mass. So understanding Newton's second law of motion, force is equal to the mass times the acceleration, which really is acceleration is equal to force divided by the mass. Okay. Same difference here, that the centripetal acceleration plays the part in defining the force that is center-seeking, the centripetal force. Okay. So hopefully we're not too lost yet. So let's continue down this idea. So now those ramifications. Centripetal acceleration is an instantaneous acceleration, meaning that every single point in which we have a changing direction, which is like 99.999999% of the time. Okay, you have the only the point 0.0001% is the snapshot you're taking when your object is moving within a circle. Centripetal acceleration is always an instantaneous vector quantity. Well, actually, I shouldn't say vector quantity in this case, and you'll see why. Centripetal acceleration is an instantaneous acceleration. It's a snapshot of something moving over a span of time, and it always acts towards the center of motion. However, it is considered a scalar quantity. Now, that's kind of weird, Mr. Sheeline. I thought that acceleration was a vector quantity. In fact, you just said it was literally 20 seconds ago. What changed? And why did you correct yourself? Well, I had to correct myself because, yeah, it's a scalar quantity. Why is it a scalar quantity? Well, let's kind of think about this and draw this out. So when we were working with one-dimensional and two-dimensional motion, we would have motion that was moving on a line. We would have a motion that was moving like this, and then like this, okay? And we drew our vectors just like this, right? And we would say, oh, well, there's the, that right there is the displacement right here, because this is where we started, this is where we ended. Okay, we worked with all that. Now, why wasn't any of that, showing acceleration as a scalar quantity? And it's because of this. Every time that we did change directions, we still maintained a particular direction right afterwards, okay? So meaning we would have, we'll say the initial here. We would have the final here. We had initial here. We had final down here. We had, initial, and actually it'd be initial from here to final, and then initial from here to here, and then final, and then initial from here to here, and then a final. You get the idea, is that each time we change direction, there was still a substantial amount of data to collect of this object moving in the new direction, okay? And that we could compare initial velocity with final velocity. Now, try to compare that to a circle. So if you, let's say, find the acceleration of the circular moving object while it's right here. Okay, well, we've got the initial velocity. What's the final? Right? What's the final? Because at this point, our velocity is tangential. Tangential. I can never pronounce that word right. And in this case, it's at this snapshot, this is the direction of its motion, technically speaking. Okay, it's not really what it's moving, but this is the direction of its velocity. Well, if we were to take a snapshot here, well, now it's right here. If we were to take a snapshot here, it's going to be right here. If it's right here, it's like this. It's like this picture that we saw back at the beginning. Okay, it's like this picture. Oops, let me get this. It's this picture. Okay? So when you have all these different snapshots, you tell me, how is it that you can compare the initial velocity with the final velocity? Well, you can't, because what you then have to try to explain to me is that on its supposed projected linear path here, you then have to tell me that there's an initial velocity here and somehow a final velocity here while it's still attached to its string, while it's still attached to the center point here, and while it's moving in a circular path. Okay, and what that means then is it can't happen, because the distance from right here is from here to here, is different from here to here. It's not possible. Okay, it's just not possible. So because of that, our acceleration is a scalar quantity. It's just magnitude. Okay. And on top of that, think about it for a second here. It's centripetal acceleration. So it is a force, it's the acceleration that is center seeking. So realistically speaking, every single acceleration is moving, technically speaking, in the same direction. Though obviously, if you were to actually put it on and show all the different radians, all the different degrees, of course, it's not the same direction, because it's got a different point in which, that it's being measured from. Meaning, on a circle here, if this is your snapshot or this is your snapshot, yes, they're moving in this direction, but they're two different spots. Who cares? In this case, who cares? What's important is the fact that it's a scalar quantity due to the fact that we're changing velocity all the time due to the change of direction. But at the same time, it's always moving towards the center. So we can basically just say, get rid of the direction. We don't need the direction. It's a scalar quantity. Let's make things easier for our brains. Okay, now, and this is important because it's going to change a bit of how we have to look at this and how we then calculate this compared to when we were just looking at, 1 and 2 dimensional motion. So anyway, if I made you more confused than you should be, make sure you have a chat with me so that we can maybe set this straight here. Okay. So centripetal acceleration is caused by a changing velocity vector. It's always changing. I've already mentioned that. It points towards the center. The acceleration, by the way, the acceleration always points towards the center of the circular path of motion. Okay, and it's always the same because when we're talking about uniform circular motion, because we're talking about something that is moving at a constant velocity, meaning every single time you would take a snapshot of that thing moving in a circular path, it will have the same velocity each time. And not only that, its radius is exactly the same. And we're gonna look at when we change the radius. We'll see what happens if when you do a test with radius being a certain distance, and then you increase it or decrease it, and we'll see what happens. Okay, so here is how we calculate it. So the magnitude of the centripetal acceleration can be calculated with this formula. It's going to be the centripetal acceleration, A sub c, is equal to tangential velocity squared over the radius. Okay, where the AC is the centripetal acceleration, V is the speed of the object, the velocity of the object really, and R is the radius of the circle. Okay, and because the direction of our centripetal acceleration is always the same, and because our velocities are always changing due to the fact of it's a changing direction, it is changing direction, it is a scalar quantity. It's just the magnitude. Okay. So here's a breakdown. Now, I provide delta S here, the arc length. I provide it here because this will be something that you'll notice. It'll be something that you notice. Oh, excuse me, yawning here. This will be something that you notice in other illustrations, and just so you know what it is, just so you're familiar with it and you're not terribly confused by it. All that is just the arc length. We're not going to be calculating arc lengths, just FYI, because the arc length is that gets into like more AP, physics territory. And that's where we really have to know our radians. We really need to know how to determine the actual the number of radians at on a particular circle. And we won't get into that. That's something that's twice the amount of work and amount of substance. So we'll just, anyway. Okay. So, and this is just to show you that this is how certain ideas are set up here when we talk about uniform circular motion. So there is a delta V, a change in tangential velocity, which we'll get into later on when we're looking at non-uniform circular motion, which we'll do a little bit. And it's just the change in velocity, realistically speaking. So if you had, as an example, if you had an object moving around in the circle and from V1 to V2, you change your velocity from V1 to V2. If it goes from, say, 10 to 5 meters per second, you would just say the change in it is 5 meters per second. That's really all you would say. It's just to understand that we do use that there can be differences, but since we're using uniform circular motion, V1 is going to equal to V2, and V2, because they're the same, we don't really have to worry about anything changing. Though, again, in non-uniform motion, it will. Okay. So that's pretty much the extent of the notes here, or maybe it's not. Let's see. When do I get into? There it is. So check your understanding number 1 and number 2 are going to be found in a separate video, just so I can actually write things out. I'll walk you through and how to solve those. So I'll have that posted along next to this one. I'm going to continue with this video and keep walking through. So make sure you complete these. Go back, try to solve those two using this formula here. Okay. And once you have that done, then come on back and we'll keep on moving. Okay. Okay. And we're going to keep on moving. Now, so using derived equations, we can calculate, so what we're getting into now is different ways that we can calculate centripetal acceleration. Okay. And we can use this, we can find this using a formula where we use period. Okay. Which period is just or we use period, pi in the radius of our circle. Okay. Now period is just the time it takes for our object to make one full resolution, one full radian, or sorry, 2 radians. And it's again, it's just the time it takes in order for your circle or the object moving in a circular path to reach, where it started. So like this. So here's the path. If we start here, period is just the time it takes in order for it to go boom, and then stop right where, either stop or to pass where it began. Okay, so that is period, and we use the capital T for period. Okay, the time it takes for our object to complete one full trip, one full resolution around the circle. Okay, so we can use this. We're going to be using this a decent amount where we can find our acceleration this way. Now, let's say we've got something that's moving super duper fast, and it's kind of hard. It's kind of hard in order to figure out just how long it takes for it to move in a circle. So what we can do is just flip it on the inverse. So instead of the time it takes for one revolution, we can do frequency, which is the number of revolutions over a particular amount of time. Okay, so for high rates of revolution, it's common to state the frequency rather than the period. And we would use this equation to show this. And again, frequency, or F, is just the number of revolutions per second in this case. So it's 1 over T. It's just literally the inverse of what period is. It's flipped. Okay. So in this case, everything's the same. The only difference is instead of having period, or dividing everything by period, now the frequency is being multiplied by your 4 times pi squared times your radius. Okay. And frequency is still squared. Okay. So we'll be using both of these equations here in order to, all 3 of them, I should say, the velocity squared over radius. We'll be using 4 pi squared times our radius times our frequency squared, and we will also be using our 4 times pi squared times radius divided by our period squared. Okay? Now, here's where we use them. Okay? So if your speed is known, so if your tangential velocity is known, well, we can just simply solve it with tangential velocity squared is divided by the radius. Okay? We can find acceleration that way. Now, let's say speed is not known, but period is known. So that's where we would use 4 times pi squared times radius divided by time squared. But then let's say if F is used in place of T, or we know that there is a bunch of different, like it's moving super quick, there's a lot of revolutions, and we time those revolutions, okay, we would use the 4 times pi squared times radius times the frequency squared. Okay, so this is where we would use them. And that's where you're going to practice them here. So go ahead, give them a whack here and check your understanding number 3 and number 4. And that's the end of the video, guys. So really, and this is why, for the most part, there was nothing for you to fill in on these notes, because it is a much more discussion, just listening kind of set of notes, because it's stuff we've worked with before. Now we're just adding them and putting them into a different context. Now, instead of a linear path or a straight line or a number of different straight lines moving in different directions, now it's a circular path that has different directions at every single snapshot that we make. Okay, so that's the end of the notes here. We're going to be getting into this on the next in-person day. This forces in circular motion. We'll be getting into, really talking about what the centripetal force is, how it is that we can calculate the centripetal force. And then we'll also get into something called the centrifugal force, which is a thing, but also not a thing all at the same time. We'll get into that, and we'll take a peek at that and make more sense of it when we get there. So that's the end of the notes here, guys. If you still have any questions for me, make sure you email me, get a hold of me on Remind, whatever you can do to get a hold of me. If not, I'll see you guys in the next one.